I'm going to introduce the final speaker, who's going to talk about data returned from the Starshot probes, live from Alpha Centauri. It's Dave Messerschmitt, a good friend of mine, Professor Emeritus of Electrical Engineering and Computer Sciences at UC Berkeley. Dave is, in the first 10 years of his career, he spent it at Bell Labs, the Bell Labs, the famous one, in the early days of communications, digital communication exploratory development. He's a co-author of 5 books on the subject, including Digital Communication, now in its 3rd edition. His doctorate is from the University of Michigan. He's a Life Fellow of the IEEE, a member of the National Academy of Engineering, which is not easy to do. And he's a recipient of, get this, the IEEE Alexander Graham Bell. Remember him? Alexander Graham Bell Medal recognizing, quote, exceptional contributions to the advancement of communication sciences and engineering, which is something we really need because the data return problem is formidable. David Messerschmitt.
Okay. Thank you very much, Jim. Obviously, everything we've done to get the sail accelerated and the spacecraft doing a pass-by by Alpha Centauri is not going to pay any dividends unless we can collect some scientific data, which is initially probably images, and get that data back to Earth. So I'll talk about the problem getting the data back to Earth. Philip Lubin and Ian Morrison and I have been having conversations, get a little closer, have been having conversations by Skype every week or bi-weekly about this problem. So a lot of the insights I'm going to discuss come out of that collaboration with Philip and with Ian. So to make it clear that the phases of the trajectory of a starshot will be the transit phase of about 20 years, the science collection phase, which will last on the order of minutes because of the high speed of the spacecraft, and then a communications phase during which we're communicating the data that's collected back to Earth. So what we're talking about now is that communications phase. As a measure of the difficulty of the problem, we can compare to outer solar system missions that go to Pluto, for example, and compare the distance to Proxima Centauri or Alpha Centauri to the distance to Pluto. And that turns out to be, the square of that ratio turns out to be about 10 to the 7th, 10 to the 8th. The square of that ratio is a measure of how much the power decreases in that electromagnetic radiation traveling that distance. So we have 7 or 8 orders of magnitude to make up compared to outer solar system missions. Where do we get those 7 or 8 orders of magnitude? Well, before I get into that, let me define one key parameter, which is going to occupy about the final third of my talk, which is the bits per photon, or the photon efficiency. So the bits per second, the data rate that we're getting back, is the bits per photon times the photons per second. And the bits per photon is an opportunity to get more data back if we can increase that parameter. And that's something that us communications people are accustomed to doing. So in what follows, I'm going to assume a benchmark of about 10 bits per photon, which is a fairly aggressive assumption. Fortunately, I'm the first speaker this morning that's made an aggressive assumption. Right? That's, I think, probably doable, but it is aggressive. So this is the only big equation in my talk, I promise. But these are all the factors that play into the relationship between received bits per second to the transmit power in watts. And of course, we can increase the bits per second by increasing the transmit wattage in direct proportion. So bits per second is proportional to power transmitted. One of those factors is 1 over d squared, which is what I just considered, the distance to Proxima Centauri or Alpha Centauri squared. That disadvantages us by 7 or 8 orders of magnitude. Where are we going to make that up? Well, we have to make it up in these other factors. One is the wavelength, and the wavelength appears in this equation twice. One is 1 over lambda squared, which is just the coupling of the transmit and receive antenna, which improves at shorter wavelengths. And the other is the factor of lambda here, which relates the energy of a photon to the energy of a photon, so relates power to number of photons. The net is 1 over lambda, so the receive bits per second to the transmit power is inversely proportional to lambda. So if we simply move from radio frequencies, which is what's used in all of the NASA missions in the solar system, to optical frequencies, we can gain about 5 orders of magnitude. So in the following, I'm going to assume 1 micron wavelength for our communications for that reason. If you want to go back to radio frequencies, you have to consider apertures that are on the order of the size of the Earth. Another factor is the product of the transmit aperture area times the receive aperture area. So that factor is going to have to be very large to make up for the distance that we're talking about. So we'll talk a lot about that number. Another is the bits per photon. The greater the photon efficiency we can achieve, the smaller the aperture we can get away with. So for example, if we increase the bits per photon by 1 order of magnitude, then we reduce the aperture area by 1 order of magnitude. And the final factor there is an efficiency factor, eta, which is various things that come into the quantum efficiency of our detection, such as the quantum efficiency of the photodetector that we're using and other factors we'll talk about later. So these are the factors that we can play with. Now, one of the things to keep in mind is during the communication phase, after we've passed the target, the distance of our spacecraft to the Earth is increasing fairly rapidly because it's moving still at 20% of the speed of light. So the rate at which we can transmit data is going down as the square of that distance. So, for example, after 20 years, the distance has doubled and the data rate is decreased by a factor of 4. And after 100 years, the data rate has gone down by a factor, down to about 3% of where it started. So if we think about transmitting data over a period of time following the encounter with the target star, then we can work backwards to figure out how much data we can get back to Earth. So that's what I do in the next view graph. In this, I've assumed that the total data volume is 100 megabits, not megabytes, but 100 megabits, 100 million bits. Where I get that number is by assuming that we have 100 images, each image 1,000 by 1,000 pixels, and each pixel 1 bit. That gives us 100 megabits. 1 bit after compression, obviously. And compression of the images is going to be an important factor, and that has to be done on the spacecraft and requires processing. If we work backwards from that 100 megabits, and if we transmit data for 1 year after the encounter, then the bit rate has to be 3.3 bits per second. If we transmit for 20 years after the encounter, the bit rate has to be 0.3 bits per second. And if we transmit for 100 years after the encounter, the bit rate can go down to 0.18 bits per second. Those bits per second are the initial bit per second at the target. And then, of course, the bit per second decreases as a square of distance. So in the following, I make a very conservative assumption that we transmit data for a long time after encounter, because that gets us the lowest bit rate and therefore decreases the aperture size. And the aperture size is really a controlling factor in the cost of the system. So I'm going to assume a data rate of about 0.2 bits per second, which assumes that we're transmitting data for like 60 years after encounter. If you don't like to wait 60 years to get all of your data back, of course you can increase the power, increase the aperture size. There's a number of factors that you can play with, but this is very conservative, and we can go up from there. The other piece of good news is that that's the time to get the data, all the data back to Earth, but we can get individual images back sooner than that by transmitting the most compelling images first. So the question is, how fast do we get the first image back, and how fast do we get all the images back? Both of those are important. So one of the things that we would like to have of the designers of the spacecraft, us communications folks, is a long half-life electrical generation using RTGs or whatever, in order to be able to extend the period of time over which we're transmitting data. And of course, we can trade that off against the received aperture size. We also like non-volatile radiation-resistant storage, and of course the spacecraft has to have a high degree of reliability to do this, keeping in mind that we will get early images back first, and so if the spacecraft fails for some reason, we will have gotten some data back. I think that the electrical generation issue is something that should be in the early proposals or RFPs from Starshot, because it strikes me that firing plutonium pellets once a week through the atmosphere has some fairly serious environmental safety concerns that should be addressed, or perhaps people have better ideas about how we can get the electrical power that we need for such a long period of time. But the plutonium, fortunately, has a half-life of about 80 or 90 years, so that will do the job if we're able to overcome the environmental concerns. Okay, so for example, if we're transmitting data back for 20 years after encounter, then we have 21 years of transit to Alpha Centauri or Proxima Centauri. We have 20 years of data transfer back. During that 20 years, we've receded to 8 light years away from Earth, so the data takes 8 years to get back. And the bottom line is, in that particular example, we get our complete data set back in 49 years after launch of the vehicle. If you want your data back faster, like 1 year of data transmission, then you need to increase the aperture area by an order of magnitude. Now, I mentioned that we can transmit one image back faster than that. There is, however, a limitation on how fast we can get one image back, and that's outages. We're going to pay 2 prices for moving from radio to optical wavelengths. One price that we're going to pay is the dimensionality of our transmit and receive arrays increases by the same 5 orders of magnitude, the precision with which we make those components. Another price we pay is that the signal is going to be heavily affected by atmospheric effects. And in particular, we're going to encounter atmospheric turbulence, daylight, weather. Now, daylight is an interesting one because the sunlight is going to tend to interfere with our optical signal due to scattering and the turbulence and the scattering both in the atmosphere and the scattering in the receive optics. So in fact, we may be able to receive signal only during during nighttime. That's an unknown at this point. But we're certainly, in any case, going to have weather events, clouds that are going to interfere with reception. And we're going to have potentially multiple probe interference, which I'll talk about in a moment. The bottom line is we can expect that the data that we're receiving back is only going to be received maybe half the time or 30% of the time, something of that order. Maybe as much as 60 or 70% of the time, we just don't know. We know how to deal with that problem. It's a problem that occurs in a lot of communication systems, but it does require that we increase the transmit data by adding redundancy that allows us to recover the images in spite of the fact that a lot of the image data has been lost. So that's a workable problem, but it increases the data rate that we have to transmit. And so for example, if the outages are 50% on average, then we need to transmit at least twice as much data to be sure that the images get back reliably. So the longer that we transmit the image in relation to the outage times, the greater the reproducibility of the outage events and the outage probability. So we're in fact going to want to transmit each image over a period of at least several years in order to average out weather events, seasonal variations, night and day, and all these factors. And it would be more comfortable if we transmit each image over a period of 10 years rather than a few years, because then we'll get more statistical reproducibility and we can reduce the amount of redundancy that we have to include in the transmission. The transmitter, of course, knows nothing about when the data is being lost, so that's all up to the receiver to make up for that. So for this reason, there's a limitation of probably at least a few years after our encounter before we can receive the complete image. So it's not as bad as the 20-year example I mentioned before, but it's not exactly instantaneous either. So in the example that I'm going to give you in a moment regarding the aperture area that we require, I'm going to use the number 0.2 bits per second data and another 0.3 bits per second of outage redundancy, giving us a total of 0.5 bits per second. And if we have 10 bits per photon, that means we're 0.05 photons per second, or in other words, we're receiving one, or detecting, I shouldn't use the word receive, I should use the word detect. We're detecting one photon every 20 seconds. Okay, so that's kind of what we're shooting for in this example. So to receive one photon every 20 seconds, I'm going to assume a wavelength of 1 micron, a transmit power of 10 milliwatts, a photon efficiency of 0.5, 50% quantum efficiency, a transmit aperture diameter of 10 centimeter, and the bottom line is then the receive aperture diameter needs to be, for this example, about 500 or 600 meters, which is on the order of the fast radio telescope in China, but of course this is optical, not radio, so it's an entirely different design challenge. Now that's undoubtedly an optimistic number because there are some factors that we have not taken into account in this simple calculation. And so we're starting at 500 or 600 meters, but it's going to go up there as we introduce other factors in our equation. Some of the things that are going to increase the aperture area are background radiation. I haven't talked about the fact that the photons we're receiving or detecting are not simply all from our Starshot, but they're also photons coming from all the stars and galaxies out there in our field of view. There's photons coming from the zodiacal debris in the solar system, in our own solar system and in the faraway solar system. And there's also potentially photons coming from the target star, unless we can resolve with our receive aperture our spacecraft from the target star. The good news is that Proxima Centauri is a relatively cool star, so it's fairly easy to deal with. Alpha Centauri will be a bigger deal in terms of the potential interference of photons coming from the star. So those things we haven't taken into account here. The good news is that the very low bit rates we're talking about, we can put in bandpass filtering in our receiver that's fairly narrow bandpass filtering on the order of 10 kilohertz or 100 kilohertz, something of that nature. And within that narrow bandwidth, there's going to be relatively little background radiation. So we're very strongly dependent upon that bandpass filtering in our design. Pointing accuracy is going to reduce the photons reaching us. The atmospheric turbulence and scattering I mentioned already. Optics losses and the detector quantum efficiency are all things that we have to worry about, and undoubtedly there are others. So the aperture area is going to increase as we start taking these various factors. But sort of our wish list of what we would like to see here is effective optical bandpass filtering with very narrow bandwidths, and that's technologically challenging. There are some technologies available, but we'd like better technology than currently available. There's going to have to be a good attitude control of the spacecraft to keep it pointed back at Earth during the communication phase. And we're going to have to build very large receive apertures, and the problems there are very similar to what Bob talked about earlier on the laser transmitter, the propulsion system. Including ray synthesis, adaptive optics, and hyper-efficient photon counting. Now there's another problem, which is that we're not going to just transmit one of these starshots. We're going to, I should say, I'm a communications person, so I transmit. We're not going to launch just one starshot. We're going to launch a starshot every week. It was suggested in Bob's talk earlier. And that means that we're going to have upwards of 1,000 or 2,000 of these. I guess it was Kevin that mentioned every week. That means that we're going to have on the order of 1,000 or 2,000 of these starshots in the communication phase at any given point in time. And a lot depends, of course, on the transmission time for each of these vehicles. So we have to separate out the communication from all of these various spacecraft that are following basically the same trajectory. This is a well-known problem in communications. You all use your cell phones along with thousands of other people at the same time using the same bandwidth, so we have some standard techniques for dealing with that. And that's the good news. The bad news is the techniques may further increase the aperture area that we require, and they certainly are going to complicate the problem of the aperture design and the receiver design. So some of the techniques that we use, I've immediately struck out the first two possibilities. One is space division. These vehicles are basically following the same trajectory, so they're all going to be the same directionality from our receive antenna. So we're not going to be able probably to separate them out by pointing angle. Time division is probably going to be way too inefficient. Time division means each spacecraft transmits at a different time for a couple of reasons, but the main reason is that spacecraft are not going to have accurate enough clocks to do that. Because we don't have an uplink, it's not going to be possible to synchronize transmissions of the different spacecraft. The technique that seems to make the most sense as a starting point is wavelength division, that each starshot transmits on a slightly different wavelength so that they don't overlap each other, and that's the technique that I will focus on. The challenge that we have in doing that is that there's frequency variation and uncertainty. So we have to have enough guard bands between these transmissions to keep them separate in the face of any uncertainties in wavelength or frequency. The transmit wavelength has some uncertainty depending on the lasers that we're using and temperature and things of that sort. Variations in speed of the spacecraft. We don't know the speed of the Starshot precisely, and the speed will affect the wavelength through the Doppler shift. And then there's gravitational redshift. That's not going to be much of a factor because by the time we're transmitting back from the during the communication phase, we're well past the target star, so we're not influenced heavily by its gravitational field. We do have Earth rotation and orbital Doppler shifts, but those are deterministic factors that can be corrected at our receiver. But they do cause a variation in frequency, and therefore they cause potentially an overlap between different bands. So there needs to be a careful consideration of all of these sources of frequency uncertainty in conjunction with different wavelengths to come up with a technique that's reliable. If we, for example, don't have enough total line width or bandwidth to transmit from all the spacecraft simultaneously, then we can get into more complicated techniques like frequency hopping, so that each spacecraft hops in frequency, and then sometimes they interfere, but those interferences are guaranteed to be limited to short periods of time. And those interferences among spacecraft then become another source of outage, which we can account for in the data rate, the raw data rate that we're transmitting. But requirements on the receive antenna array are pretty severe due to all of this, and that is that they have to be frequency agile. So we can't depend on the signal coming back from the individual star shots to be at a single known frequency, but it's going to vary. And we need multi-channel bandpass filtering to separate out the various spacecraft that are transmitting simultaneously. And the design of that receiver array is already complicated. This is a considerable complication. Now, everything I've talked about so far assumes photon counting, and this is the preferred way of building a receiver for the signal. And the basic idea of photon counting is to have a photo detector preceded by optical bandpass filtering, and then a baseband signal that we can process to recover the bits. There is an alternative that simplifies a lot of the problems that I was mentioning earlier, and that is to do heterodyne. So I'll talk about heterodyne in just a moment. The photon counting is the preferred technique, and it's going to be a severe technological challenge to figure out how to make this frequency agile, multiple channel, very high Q, narrow bandwidth, bandpass filtering, etc. So this has a lot of challenges associated with it, and I'm happy to be a communications person and not a photonics person, so I don't have to figure all this out. But one of the technologies that would make things a whole lot simpler if it's available is if our detector told us the energy of the photons as well as the time of arrival, the energy being related to their wavelength. Then we could do our subsequent processing without this narrow bandpass filtering. Heterodyne makes a lot of these problems easier because it shifts them to the microwave region rather than the optical region. And the basic idea is to have a high-power local oscillator that's mixed with the received signal at the input to the photodetector, which is a square law detector, and the result is that we get a signal at the difference frequency, which can be arranged as in the microwave. And in that case, then we can do all this bandpass filtering and frequency agility and everything in the microwave range, which would be a whole lot easier. This approach, while it's easier, has a severe problem with it I'll talk about later. Namely, we will have to increase the aperture area by an order of magnitude or so if we use this technique relative to photon counting. Now, one of the things that I when I mentioned to my physicist friends we're going to get 10 bits per photon, the typical first question is, how in the world are you going to do that? Don't you require at least one photon for each bit of information? Well, this diagram sort of gives one of the basic idea, although it's not a practical technique for various reasons. The basic idea is if we increase the bandwidth of the signal, and so we can arrange for this one photon to arrive in one of a number of time slots, and in particular, if it arrives in one of 2 to the 10th time slots, which is 1024, then the time slot that photon arrives in communicates 10 bits of information. So the basic idea is that if we can use the timing of the arrival of photons rather than just the arrival or non-arrival of a photon, we can increase the number of bits of information that are communicated. There is, of course, the uncertainty principle to worry about, the Heisenberg uncertainty principle. If we carry this too far, we're not going to be able to get that kind of timing accuracy. But that's many, many orders of magnitude away from where we're operating in this system. Well, this is not a practical technique because it doesn't take into account the statistics of photon arrival, which are Poisson statistics of photon arrivals. But it does communicate an essential idea, which is to use timing rather than just the arrival or non-arrival of a photon to communicate information. So let me say a few words about how us communication folks achieve high photon efficiency. And the basic idea is the following. If we take our scientific data and we take a number of bits of the scientific data, like thousands or tens of thousands of bits of scientific data, and we map those large number of bits into an intensity modulation at the transmit lasers, and we're going to use on-off modulation. So the transmit laser is either on or it's off. So we switch the transmit laser on and off in response to the large number of scientific data bits, okay? At the receiver, then we get individual photon events. We don't see the intensity of the transmit waveform. We see individual photon arrivals. But those photon arrivals occur only during the on period in the absence of background information, neglecting background radiation for a moment. Those photon arrivals only occur during the on state of the transmit laser. And so with the receiver, we do photon counting. And then the next thing we do is we look at the pattern of photons that have arrived and we match that to the possible intensity waveforms at the transmitter. And that number of possible waveforms may be very large. If, for example, we have 1,000 bits that were mapped into an intensity waveform, it might be 2 to the 1,000 potentially different intensity waveforms. So we do a matching of the intensity waveforms to the photon counts that we actually see, and from that we can recover the scientific data. So at 10 bits per photon, to give a concrete example, we take 10,000 bits of the scientific data, we transmit an intensity waveform at a power level which results in 1,000 detected photons at the receiver. And from those 1,000 detected photons, we recover our 10,000 bits of data. So it's not, the way to think of it is that we're not transmitting 10 bits of information with one photon, but rather we're transmitting 10,000 bits of information with 1,000 photons. And every one of those 10,000 bits is dependent upon all 1,000 photons that were detected, okay? As is all the other bits among the 10,000. So this is a challenging thing to implement, as you could imagine. In fact, it was known that we could do this 70 years ago, and it took about 50 years of advances in what's basically a mathematical field. Communications is really a mathematical science, not a physical science. It's has nothing to do with physics. Physics and electronics face the sort of the environment in which we operate. But playing these kind of games is a mathematical game because we're operating in a space of 10,000 dimensions, and to do that we require mathematical structure. So it's mathematicians that work on these problems, not physicists. One of the questions that arises in this diagram is there some limit? You know, I said 1,000. Could we get away with 500 or 100 or 1 photon? There must be some kind of a limit on what we can accomplish here. And there is, which is well understood. What is the smallest number of photons that we can get away with is the question. And this depends upon the statistics of the quantum statistics of the photon detection. So to tell you what the fundamental limit is, I have to define another parameter first, which is the peak to average ratio, or PAR. So if we're transmitting this intensity waveform on-off, the peak to average ratio is the peak power of the waveform to the average power of the waveform. Okay, so this is the fundamental limit that we're operating on. The theorem I'm referring to here was proved about 30 years ago. The theorem is about 40 pages long, so it's not a simple thing to prove. But it was shown that if we're operating in the blue shaded region, that it's possible to achieve any level of reliability using the basic scheme that I described as we increase the number of bits that we map into the intensity waveform. If, on the other hand, we're in the outside of the blue region, then it's impossible to achieve reliable communication. And the blue region is defined by the equation that the bits per photon has to be less than the log to the base 2 of the peak to average ratio. So this tells us something important, and that is that peak to average ratio is one of the key characteristics of our transmit laser system that's going to determine the bits per photon that we can achieve. So as one data point, if we're operating at a peak to average ratio of 2 to the 10th, which is 1,024, so that means that out of every 1,000 time slots, there's only one pulse out of the laser, then the fundamental limit is 10 bits per photon. Okay? So this is the level I'm going to operate with, and we're going to work at a peak to average ratio of 1,024. So our laser power peak is 1,000 times the average power of our laser at our transmitter. The average power of the laser at our transmitter, of course, is determined by the electrical power that's available on the spacecraft, and the peak power is determined by laser diode and the optics system. And the requirement that we would put on the people that are designing the transmitter is we would very much, as communication folks, we would very much like it if they're able to figure out how to get greater peak power out of the laser, which means do things like ganging lasers together and coupling them through an optical subsystem and so forth. So what I'm going to do in the next few slides is to fill in this table, which is the aperture size as a function of the technique that we use in the coding. That process I described earlier is called coding. The fundamental limit, if we have a peak to average ratio of 1,000, is 1,024 specifically, is 10 bits per photon. And that was the number I used earlier, and that gives us the 565 meter aperture diameter, which I gave earlier. So that's kind of the fundamental limit that we're working toward with this peak to average ratio. Keeping in mind, if our spacecraft designers are able to increase that peak to average ratio, we can increase that number. And it goes up as a log. Now, to come up with a concrete technique, let's start with the simplest thing we can imagine. The simplest technique we can imagine, which is called on-off keying, is that our laser transmits a 1-bit with a pulse, and it transmits a 0-bit with no pulse. Okay, so it turns out, and I won't go through the details, but if we're shooting for a reliability of 10 to the minus 7th error probability, which allows us to get a whole image back pretty reliably, then it turns out that the bits per photon for this technique is 1/8. So we get 1/8 of a bit per photon. So we can fill in one row of our table. Using this on-off keying approach, we can get 1/8 of a bit per photon. And if we plug in our equation for receive aperture size, we end up with 5.1 kilometer aperture. Okay, so you'll notice there's a big gap between 2 orders of magnitude in aperture area between this on-off keying approach and what can be fundamentally achieved. Let's get a little bit more sophisticated and use something called pulse position modulation. And in this example I've given here, we divide the bits that we're transmitting up into groups of 3 bits, and then instead of transmitting those bits independently, serially as on-off pulses, we transmit 1 pulse in one of 8 time slots. Okay, so there's a couple features of this that suggest that it might be a good thing to do. The primary one being that the peak to average ratio is much higher for this approach. And particularly if we extend this, say, to 10 bits per frame and 1,024 time slots, then the peak to average ratio is much greater, and we know that peak to average ratio is associated with high photon efficiency. And the reason that it's associated with high photon efficiency is we're communicating the information through the timing of the pulses, and we get, in this case, 3 bits of information for a single pulse instead of requiring 1 pulse per bit. Okay, so if we work out what is the bits per photon, the photon efficiency that we can achieve with this technique, we get the red dots, which correspond to different frame lengths. And basically those red dots follow a trajectory which is 1/16 of the fundamental limit. So we're still, with this technique, pulse position modulation, we're still a factor of 16 larger aperture area than the fundamental limit tells us is necessary. So we can fill in another row of our table. The aperture size with this pulse position modulation comes down to 2.3 kilometers. That's still a large aperture compared to the fundamental limit of 565 kilometers. So now what we'd like to do is improve the system further. And there are 2 ways that we can improve the photon efficiency. One is to move up that pulse peak to average ratio curve, have our electronics and photonics designers giving us higher and higher peak to average ratios in our transmitter, and stick with the pulse position modulation. We do want, in fact, higher peak to average ratios in the transmitter, but mainly because that increases our headroom for improving it in the vertical direction toward the fundamental limit. The other direction we can move is vertically toward the fundamental limit, but keeping the peak to average ratio constant. And that gives us a much bigger opportunity to improve the bits per photon. And the name of the game there is mathematics, algorithms, and processing in order to do that. The key word there is processing. This is going to require processing in our spacecraft in order to do that. The good news is that the processing is highly asymmetrical between transmitter and receiver. And in fact, most of the processing is in the receiver. The transmit processing is relatively simple. So the receiver processing, of course, is on Earth, so we're not concerned about electrical power, and we're not even concerned about the time that it takes to do that processing, because this is not a real-time system. So the processing that's going to be required on spacecraft is fairly modest. Okay, well, hopefully less than that. So I'd like to try to give you a sense of how we communications people do that, move vertically through mathematics and processing without getting into the mathematics part. So the basic idea would be something like the following. Start with 1,000 scientific data bits. We do what's called error correction coding, which expands the number of bits to 10,000. Okay, so we've expanded the number of bits by a factor of 10. That means for every single data bit, there's 9 bits of redundancy, and those 9 bits of redundancy are used to correct errors. Okay? Then we have now for every 1,000 scientific data bits, 1,000 bits for transmission, which means that we require 1,000 10-bit pulse position modulation frames. So the number of data bits per ppm frame is one data bit per frame, even though each frame is transmitting 9 bits. 10 bits, 9 of those bits is redundancy, and 1 bit is a data bit from our scientific data. Since we're operating, hopefully, at a 10-to-1 bits per photon, that means that there's 1 photon for every 10 frames. So there will be 1 detected photon to receiver for every 10 ppm frames. So the erasure, we call the erasure probability, is 90%. That is, 90% of the frames are not even observed at the receiver because they have 0 photons coming in, and only 1 out of 10 of the frames are even observed at the receiver. Then we take those bits coming out with all of those erasures, and we do error correction decoding, recovering our 1,000 scientific bits with hopefully an error probability of 10 to the minus 7. Okay, so there's 2 points here. We've created a system with serious unreliability, like 90% error probability, by expanding the number of bits with this redundancy. And also we've increased the bandwidth of the signal substantially because we're transmitting a lot more bits than our scientific data bits. So in fact, the bandwidth in this case turns out to be 1,000 times greater than the data rate for the scientific data. I think in a practical system, it'll be more like 10,000 times larger. One of the important points then that comes out of this example is in communications, we always like to expand bandwidth. If we hold the receive power constant in photons per second, and we would like to increase the throughput data rate that we achieve reliably, we do that by increasing the bandwidth of the signal. I mention that because communication people and astronomers often talk past each other because astronomers are always trying to narrow the bandwidth to limit the background radiation, and us communication folks always want to expand the bandwidth. And that's in spite of the fact that there's greater background noise coming in the receiver. It's still a win-win. So my colleague Ian Morrison ran an example using something called Reed-Solomon coding in the context of that system that I just described. Reed-Solomon coding is a simple technique. It's very old. We can do better today, but it was very easy to do, which is why he did it. And for your information, Reed-Solomon coding flew on the Voyager spacecraft back in 1977, together with a layer of convolutional coding on top. It's also, if you've ever watched DVDs or listened to music on CDs, what you were listening to was played through a Reed-Solomon decoder. And if you've ever watched TV, Reed-Solomon coding and decoding is incorporated in both the over-the-air and the cable TV systems that we're using today. So using that technique and optimizing it for a peak-to-average ratio of 10, Ian was able to get up to about 6.8 bits per photon. So this is the final row in my table, reducing the aperture size to 684 meters. And that 684 can be reduced further by using more sophisticated coding techniques, but that's an early indication of what we can do. So the trade-offs that we're looking at here, if we're if we have a fixed transmit power, fixed data rate, and we want to reduce the aperture area, how do we do that? The aperture area being the dominant cost in the system. We want to increase the peak to average ratio in the transmitter, which is a job for the electronics and photonics designers. We'd like to increase the bandwidth of the system, but the bandwidth here is still going to be very narrow at optical wavelengths. It's going to be on the order of 10 kilohertz, which is very narrow. And we like to incorporate error control processing, and the key term there is processing, because that means that there needs to be processing power in our spacecraft for doing that. Why avoid heterodyne? The reason is that heterodyne is limited to 1.44 bits per photon, and the problem with heterodyne is we have this high power laser local oscillator, which is basically a broadband noise source in our receiver. And so it limits the bits per photon that can be achieved. And so it's 1.44 times the quantum efficiency, which means that in practice it'll be something like a half of a photon per half of a bit per photon. So we have an increase of an order of magnitude in the aperture, at least, if we use heterodyning relative to photon counting. So, and just the final conclusions are that the communications is a very challenging problem because of the 10 to the 7th or 10 to the 8th factor that we have to overcome. It may be feasible at very low data rates and with large latencies. And latencies in terms of the time to get our data back to Earth. Kind of the biggest pain points are attitude control and pointing accuracy, large apertures, synthesis and adaptation, frequency agility and optical bandpass filtering in conjunction with photon counting, and the channel coding for improving the bits per photon. So those are all areas that need to be worked on, and I would also mention the power source and the problem of environmental issues behind transmitting radioactive pellets in this fashion. So I don't know if there's time for any questions. I guess we could trade off between lunch and questions.
Yeah, there is, and that's when you're... Thank you, Dave. That's a trade-off we're all going to have to make individually. I want to ask a question. You've shown us that you could reduce the aperture size to substantially less than the transmitter aperture size by using these coding methods, optimistically. You've also shown us that bringing back data from multiple spacecraft, we will be listening a lot of the time. So doesn't it actually make sense to have them be separate apertures so they don't interfere with their operations? Because we're not going to stop transmitting and launching, and we're going to increasingly be listening. So down there, decades into the future, wouldn't it be logical to have separate apertures for transmit and receive?
Well, I would say that the sharing of the facility between transmit and receive, let's say propulsion and receive, is not a big problem because we're only going to be doing a few minutes of propulsion once a week or something of that nature. So it's another source of outage probability. And I think that outage probability is something we can deal with, and that level of outage will have a fairly minor effect on the data rate we can achieve. But the aperture size that I described was very optimistic because I wasn't taking into account a lot of factors, principally atmospheric effects. So that aperture size will have to increase. And by the time we take account of all of those factors, we may get up to the same level as the propulsion transmit laser aperture size. And if we don't, and we want to use the same aperture for transmit and receive, then there's an opportunity to either increase data rate and get more scientific data back through increasing data rate or reducing the time of transmission. So that would be very good news. But I like to start with a conservative assumption and then move in the direction of reality.
Give us an estimate on how good the quality of the picture is likely to be from the Starship camera And how long would it take after flyby to get back a high quality picture that a newspaper publisher would put on the front page of or put on a website? You know, how long and how good how long will it take to get a good picture back after flyby, and how good a picture can we expect?
He's saying, how long does it take to get a really high quality image back?
Oh, well, you know, I was assuming a relatively low quality image. I would say 1,000 pixels by 1,000 pixels, 1 bit per pixel. If you want 10 times that much data per image, then of course the data rate has to increase by a factor of 10. Or something else has to give, higher average power. And you, of course, can increase the transmission time to get the data back, so you'll get a longer wait until you get data back. So, well, I think that we can expect a medium quality image 3 years after flyby, and then it goes up from there.
Next question?
Do electrified atmospheric waveguides exist between star systems that might be utilized in the same fashion as radio engineers do in the Earth's environment?
I think the answer is no. Do you understand the question?
Yeah, I'm not sure I understand.
There aren't
that
any electrified, essentially natural waveguides to assist us
No,
in
there's
the
no.
interstellar medium.
Not to our knowledge.
It's a free space transmission. I guess I'm not understanding your.
Well, that's what I'm asking, if there are any known...
The answer is no. No. Next question?
In all of these coding schemes, I presume you need clock pulses or some kind of synchronization.
Speak up a little louder.
In all of these coding schemes, I presume you need some kind of clock pulses or synchronization, time synchronization to start to know when the bits come in particular bins. How are you handling the clock pulses or the synchronization pulses?
Yeah, the question I think is synchronization. Any communication system has several synchronization issues. One is to synchronize to the wavelength of the received signal. That's called carrier recovery. So we have to do that. We have to track the spacecraft's received wavelength, which is going to vary somewhat due to velocity and other things. Secondly, we have to synchronize up to the pulse position frames that were described, and that's called timing recovery. And the third thing is that we have to synchronize up to the coding, in terms of what the bits mean, the semantics of the semantics of the bits. All of those are known problems that we can deal with, but they will require a lot of processing. So the good news is that this is not a real-time system. So in the receiver, we can record the time that photons are received and possibly their energies, and record that in an archive, and then we can process it offline to recover the data. And that recovery of the data can, there's no time limit on how long it takes to do that. So the primary record of the mission will be the received photon times. That's what documents the mission. And then the processing of those photon events to recover the data is something that occurs offline. For example, through BOINC or some supercomputer center or something of that nature. Mm-hmm.
The one physics effect that wasn't in your mathematics was dispersion. It's not a perfect vacuum, so you're going to have some dispersive effect in the transmission over that distance.
Well, yes, the interstellar space is dispersive due to hydrogen ions and electrons and so on. However, those effects are pretty small at optical wavelengths.
How do you know that? Is there any way?
From
Have
astronomy.
we ever made a measurement?
Astronomy's measured it quite accurately.
Yeah, pulsar astronomy has measured this at radio wavelengths, and optical astronomers measure this at optical wavelengths. Because there are pulse sources out there in the universe that you can look at and then look at the dispersive effects. But optical is a lot better than radio. That's one advantage of doing optical.
Yeah.
The other thing is we're going a pretty short distance. those kinds of effects are generally not seen until you get out several hundred light years or greater.
If you have a receiving instrument with an aperture of something approaching a kilometer, why are you bothering to send a probe to Alpha Centauri at all? Why can't you just observe Alpha Centauri with your giant instrument?
Well, yeah, I think that's a good question. And if you look at what kind of resolutions you could have, Phil Lubin sitting in the back there is very eloquent on this point. If you observe at a comparable resolution to what Starshot can see, the planets, then that will take an aperture that's vastly bigger than what we're talking about here. You can tell that from the exoplanet research, which is just detecting the fact that there is a planet and sort of the rough parameters of its mass and its orbit, and it's doing that based upon our existing instrumentation, and we're not able to do any better. So yes, but there are ideas using gravitational lensing, for example, which is one of the Sagan sessions in this conference. With gravitational lensing, there's a potential to actually image planets, from our vantage rather than having to send a spaceship. But that's a good question.
Let me offer another answer. We're not doing that because we're not funded to do that. We're funded to make missions and to get out there and explore, not simply to observe.
Would the nanoships communicate back during the 20-year transit time? Are there findings that they would gather during their transit that they would transmit back?
Can they transmit back en route?
Well, the transit time, I think, was mentioned earlier, is on the order of minutes, because we're working at...
I meant the
Oh, the
20-year,
transit
during
time.
the 20-year period.
Oh, I'm sorry, not
during the
not
20-year period, would they be
not the
pinging
flyby?
back?
Yeah. Yes, certainly we could transmit during the transit time, but we would have no data to transmit other than what we collect in that interstellar region.
Right.
So if we have instrumentation on the spacecraft that's gathering information about radiation or whatever in the interstellar medium, then yes, of course, we would have an opportunity to transmit that back. And there would be essentially no cost of doing so because we have the electrical power and so on. And we're actually closer to Earth, so.
And just a general question, short, Jim.
Let me add one more short answer. On spacecraft diagnostic information would be useful to send back.
Yep,
You
definitely.
wanted to say?
Well, just a follow-up question, and it's more general. Apollo cost $100 billion, $10 billion in today's money, right? $10 billion seems like chump change. Given the potential spin-offs that the breakthrough Starshot system would create commercially, has consideration been given to the CapEx benefits of doing this?
The benefits of doing what exactly?
Of the Starshot, of creating new laser systems, of creating new communication
Oh,
technologies.
you're thinking of the other
commercially.
the spin-offs.
I'm thinking of the spin-offs
The
commercially.
spin-offs.
Yeah.
Oh, there'd be a lot of spin-offs.
Yeah.
And that isn't taken into account in the cost of Apollo. The benefits don't get accounted for, at least I haven't seen such an accounting, but should be. And they drove computing technology. They drove many technologies. There would be things, lots of things driven by Starshot technologies. And in fact, I think the whole exploration of and the development of the solar system will be advanced by this. And there's no way to put an estimate on that, but it's probably beyond our imagining, and it's certainly beyond this horizon.
I also think that they want to be, that the funders want to be more broad than,
One mission.
they don't want to capitalize on the discoveries they make for their own profit. They think this is a human effort. This is an effort of the entire planet. So they want to be as open and sharing as they can with the IP. It's a really hard thing to do, to be able to fund people to do work, and yet distribute the IP. That this is we wrestle.
Which goes straight to the heart of the altruistic beacon discussions that you've written about,
Yes.
a lot about.
Yes.
So as an altruistic enterprise, great, but I mean, you can wash out some of the costs.
There is certainly, as what Pete's saying, is that there is an aspect of the Breakthrough Foundation that is altruistic. And with that remark, this session is closed. Good day.